Today we have main topic, the shortest path. And so, do you remember any connection between shortest path and previous algorithms? Do you remember any connection between previous topics, BFS and DFS, and shortest path? And do you remember main problem that we say that BFS can be usable in the common way to solve the shortest path problem?
It will just take a lot of time.
No, it's not the main problem of the BFS. Yeah, because we use it only on weight graph. Yep. And firstly, we say that weighted graph, it is graph with weights on the edges of it. Yep. And so we say that we have a function v that set for each edge the number that have their real number. Okay. And what we can say about this graph? We say that it is directed graph, of course, yeah. And we see that we can have strongly connected components that have more than one vertices. Yep. And okay, we say that it is some. There are some problems that connected with cycles in directed graph, or sometimes later. Okay, and about first task that we solved today, about single source shortest path, we say that we want to find all ways from the source that is given vertex, and all others vertices. Okay, and in the end of our solution, we can have, for example, the tree of shortest path between S and other vertices. Okay, and we say that delta of S and V, it is the length of the shortest path between S and other vertex D, V. Okay, and if we have if we fix vertex S, we denote D of V as delta of SV. Okay. Okay. And firstly, about bad cases of weighted directed graph. Yep. It's about negative weight cycles. What can you say about a graph with negative weight cycle? For example, we have example on the board with some vertices that connected into one cycle that have in some negative sum. Yep. And what can you say about path, the shortest path between, for example, S and this vertex? The shortest path. Yeah. Okay. And
there is only one path.
Only one, yeah. There is. Okay. And if we solve this task, we say that we can use each edge more than one time. Yep. Of course, if we can use only one time each edge, it is one path between S and this vertex, yeah? But when we say that we want to solve the task with the shortest path between S and other vertices, we can use each edge more than one time. And for example, if we have negative weight cycle, we can use it, we go through it, yep, more than one time. And if we have this negative weight cycle, for example, if we go around it, for example, 1000 times, yep, we have minus 14,000 weight of it, yeah, and we can find the way from the source and other vertex with minus infinity weight of it, yep, for example. If we have any real number, we can find the path with the weight that is minor than the real number. Yep. And so we cannot solve the problem of finding the shortest path between S and other vertices if we have a negative weight cycle in the graph. Okay, so of course in the common way we need to understand if we have negative weight cycle in our graph or no, and if we have no negative weight cycle, we can solve this problem. Okay.
If we have negative weight cycle, what?
We need to solve the problem of the shortest path problem. Of course, if we have negative weight cycle, we cannot solve the finding problem between S and other vertices. But if we have graph without negative weight cycle, we can solve it, and we need to solve it. Okay.
Is it that? Is it fine to have negative weight edge, but a non-negative
Cycles.
Yeah.
Yeah, of course, but we'll see that there are some algorithms that can be useful only in way with graphs with positive weights. Okay, shortest path only for weight graphs. Yes, of course, because if we have unweighted graph, we can say that each edges have, for example, one weight. Yep, we can say that weight of all edges is equal to 1, and then solve it with algorithms that solve the shortest path problem of directed weighted graphs. Okay. So, of course, for example, in this graph we have negative edges. Yep. But we can solve problem to find paths between S and other vertices because we have no any negative weighted cycles in this graph. Yeah.
So in this one we can use binom and BFS.
But BFS works only with unweighted graph. And of course, we can say if there are some edges with number more than 1, we can cut into 2 edges, for example, or cut into 3. But if you have number equal to square of 2, in which number edges you need to cut it? Of course, if it is integer numbers, yeah, you can divide it. For example, if you have edge from R to D with weight equal to 7. Yeah, you can divide it into 7 edges that have weights equal to 1, and use BFS then. But of course, your graph will be exponential extended, and it makes a lot of problems with it. So we need to understand some algorithms that works with weighted graphs. Okay. So if we have no if we have the shortest path between S and other vertex Vn, for example, we can say that any subpath of this path will be the shortest path between endpoints of the path. Okay, and this is proof about it, because, for example, if we have any shorter path between V with index E and V with index G, we can change this subpath with P and then make the shorter path between S and Vn, and that is contradiction. Okay, so it is about subpaths, and so when we solve the problem of single source shortest path, we get tree, because any the shortest path between S and inner vertices in this graph, we can say that, okay, we have path, the shortest path between S, for example, and 14 vertex, yeah, and the shortest path between S and 6 vertex will be subpath of this path. Okay. So of course, if we want to find the shortest path between given vertex S and other vertices, we can find tree of the shortest path. Okay, and we will find algorithms that results the shortest path that has as a result tree of the shortest path. Okay, so it's about metrics in the graph. We of course set some properties of it in the first lecture. Remember it? That if we have delta of S and V as the shortest path between S and V, we can say that there is triangle inequality. Okay. Okay, so about algorithms. All today's algorithms contain relaxation operation in it. What about it? I can draw a small picture of the bot. For example, we have S and have two vertices O and V. And we know that we have some paths between S and V that has weight equal to D of O. Okay? And we have some paths between S and V that has weight equal to d of V. Okay, and if we have edge between U and V with weight W, we can say that if dV bigger than d of U plus delta of delta plus weight of this edge, we can say that if we connect S with V using this path, it will be shorter than the path that we have from S to V. So we can say that we have shorter path between S and V. I use coloring here. We can go to the V using paths from the S to U number. Okay. So we have shorter paths, and then we set new d of V equal to d of U plus weight of UV. Okay? It is operation names as relaxation of H UV. Okay? And today we will use it a lot and say that we relax some edges and then get new distances from S to other vertices. And in the end of algorithm, we prove that distances is equal to the length of the shortest path between S and other vertices. Okay? And initially, in the most numbers of the algorithms that we talk today, we say that d of V will be bigger or equal than d from S to V, delta from S to V. That is equal to the weight of the shortest path between S and V. Yep. And it is the invariant that we need to meet with it in each step of the algorithm. Okay. So if we use relax operation, and if distances between U and S and between V and S bigger than the shortest distances, then we can say that new distance between V and S will be bigger than distances between S and V because of triangle inequality. Because of it. Okay? Do you understand why if we have triangle inequality, we can say that the new number of d of V is equal to, will be bigger than delta from S to V.
The new number?
The new number d of V. I can color it this. Why it is bigger than delta from S to V?
Here from the inequality here, it should be equal, not yeah, here it's included. We can say that it's equal.
It's equal to what?
The shortest path here, what is the shortest path
In this graph? We don't know what is the shortest path, but we know initially that there is path between S and U that has weight equal to d of U, and we have path from S to V that has weight equal to d of V. And why, if we set d of V equal to d of U plus weight of U and V, we can say that it is bigger or equal to delta from S to V. Because we can say that it is bigger or equal than delta from U to V, because it is path between U and V, and the shortest path will be equal or smaller than weight of its edge. Understandable? Yeah? Because it is path between U and V. One edge, it is two paths. As any path, path can contain only one edge. It's normal. Okay, and we can say that initially d of U is bigger than or equal than delta from S to U. Yeah? Understandable. And then we can say that the sum of it will be bigger than delta from S to V because of triangle inequality. So it is invariant of relaxed operation. Okay, so it's about relaxation and we use it a lot today. So you need to remember it. And firstly, we'll talk about a simple example of graphs that has a very simple way to solve the shortest path problem. It is a directed acyclic graph. Remember it? And of course, we say that if our graph contains a negative weight cycle, it is a problem for us. But directed acyclic graph contains no cycle. Yeah, so there are no negative weighted cycle, so we can solve it. Okay, and how to solve it? We use topological sorts to order the vertices, and then we can start with the vertex that have the bigger the small number and go to the sink of the order. Yeah, and every time we repeat the relaxation operation for each edges that connect with that incident to our vertex. You can see it. Yeah. For example, I use topological sort. Do you see the slide? Yes. It is. For the I didn't understand the definition of weighted by the way. Masoud, about weighted of the graph, we can say that our graph is weighted if we have the function weight that say for each edge which real number is equal to it. It's about definition. And about the slide, if you don't see any of these numbers, you can open it on your laptop. I send it into the chat and see numbers. Okay, and firstly we use topological sorts, and you can see that each vertex has its own number. Yeah, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you order it by these numbers, you see that each edge connects left vertex with right vertex because of property of topological sorts. Remember it? That you can draw your I can draw how many 10 we have 10 vertices, yeah. 1, I use other color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. And I can draw all these edges, for example, from one to from first vertex to second and third. Yep. We have these two edges. We have edges between second and fifth vertex. From third and fourth and fifth, yeah. From fifth and sixth to other, yeah, vertices that have bigger number than 6, and from 8 to 9, yeah. And you can see that is the order when each edge connects left vertex with right, have direction equal to order of the vertices. Yep. It is the result of topological sort. Remember it. Nice. Okay. And so initially we say that we know only one distance before S and other vertices. Between S and S, of course. We say that it is equal to 0. Yeah? And other vertices have distance equal to infinity. So then we start with vertex 1 and relax all edges that incident to this vertex. So we say that if this vertex has distance bigger than this distance plus weight of the edge, we set this distance the new distance because of the relax operation. Remember it. But for the first and second vertex, we see that the distance before source and these vertices is equal to infinite. So if condition will be not true. Yeah. So it changes nothing, these two steps. Yeah. Then when we get source and relax edges that start in the source, we see that fourth and fifth vertices have a distance d equal to infinite number. You see it? It is infinite and it is infinite. But we see that distance between S and S equal to 0. We have h equal to -3 and -1 between source and fourth vertex and fifth vertex. And so we change d of fourth and fifth vertex. Yeah? And set it is equal to -3. It is equal to sum of 0 and -3. And -1, it is new distance from fifth vertex and source, because it is equal to 0 plus -1, 2. Okay? Then we relax new, and okay, of course, we said that precedence of fourth and the fifth vertex will be source. Yeah, it's about links between vertices and previous vertex in the path from the source to it. Yeah, you remember the tree that we need to get in the result. Yeah, so in this step we say that okay, we need to relax fourth vertex and relax edge that connect fourth and fifth vertex. So we see that -3 plus -2 is equal to -5 and smaller than -1 that we have. Yeah? After fourth step of our algorithm, we have distance of fifth is equal to -1. And then we say that if we relax this edge, -3 plus -2 is smaller than -1. Then we set new distance between fifth and source. Okay, you have this path between source and fifth vertex.
Here we have -3 and -2 are going back.
It is smaller than this way, from the source to the fifth vertex. So we change, firstly we change the precedence for the fifth, and we change the distance from the fifth to the source. Okay?
Will be 3?
Will be 4. Will be 4, yeah. Because the shortest path between source and fifth vertex contains 4 in it. Okay, then we repeat it for other vertices, we repeat it for fifth vertex, and relax this edge and set for the sixth vertex that it has distance to the source equal to 10, because -5 plus 15 is equal to 10. Yeah.
Can you please apply the relaxation on one of these? I just want to know dv, dw, du, and w.
How it works? Yeah.
Yes, exactly. How which one is which one?
Okay, we can see. I will draw the weights of this graph. Yeah. It's equal to 4, 3. Then it's equal to -1. From we have this h2. Yeah. -3, -2, etc. Yep. Okay, and then we want to we know that initially distance is equal to 0 for the source and infinite to other vertices. It is a part of the algorithm. Yep. Then, when we relax some edges, we get new distances from the source to the other vertices. Firstly, when we relax this edge, we say this U, V, and weight of V is equal to -1. So the red numbers is equal to d of v. Yeah, red numbers is equal to d of v. That is array, for example, of the numbers of the distances between vertices and source. Then we see for the relax operation, yeah, if d of v bigger than d of u plus weight of edge between u and v, we see that d of v is equal to plus infinite bigger than 0 plus -1. Then we set d of v equal to this sum, -1. And then we say that it is the procedure in the next row, first row. That procedure of vertex v is equal to u. Now it is the third vertex. Okay?
Yes.
So then, Vertex, can I erase some of these numbers? Okay. Then relax this edge and get distance of the first vertex is equal to -3. It is understandable too. Then we have -3, -1, and we have already relaxed these edges. Yes. Then we want to relax this edge from the fourth vertex to the fifth.
Why?
First one?
Yes, from 3 to 4.
From 3 to 4. We relax it after we relax this edge. Relax all the edges incident to the third vertex. If you want the algorithm, it is the shorter explanation of the algorithm. We relax all the edges that are incident to the vertex. Then we repeat it to the next vertex.
We move again from the beginning. For example, and we pass from 3 to 4 again.
Yeah.
How can we, what is the condition that we check to say that it is relaxed or not?
We relax all edges, but it is important what is the way that we relax edges.
Yes, I mean.
And order of relaxation of edges is equal to order of the vertex that's in the start of the edge.
I understand
Okay.
this. I just want, but if we, for any reason,
Mhm.
we pass again from 3 to 4,
Mhm.
and we have a condition checking if it is relaxed or not.
Mhm.
Because is it every time we pass from 3 to 4, we relax it again
Mhm.
or no?
We relax this edge only one time.
So the second time, we don't relax it.
Yeah.
Why?
Of course.
What is the condition that is?
We relax all edges only one time.
Yes, but there's no something like condition that is happening so we relax or not relax.
Yes, because because we have no conditions to relax the edge. We relax all the edges, but only one time. Do you understand the question of the colleague? How many times we relax each edge? One time. Only one time.
Pass it again. What are we checking?
I don't think we pass again.
For any reason, we pass again. Is there
Really fast. Like, I think it doesn't come to the same note 2 times.
It's not the same.
The same age 2 times, right?
Hmm?
It doesn't come to the same age 2 times.
Yeah, of course. It is understandable why we change the distance between fifth vertex and third, because we find new way from. Oh, do we have any questions? No. I don't hear you well. Can you text your question, please?
Maybe the voice is.
Hmm?
Maybe the voice is.
Is it clear now?
Oh, okay. I hear you. Yeah, I hear you.
So we visit every edge only once, but after every visit, the number of the edge, the number of the vertex changes, right?
The number that we have after topological sorts, the numbers don't change. You can see that each vertex has its own number and it is constant. But we change the distance between vertex and source.
Yes, I mean the distance. I mean.
Yeah, we can change the distance after we relax edge.
Yes. Thank you.
Okay. Okay. All is understandable now. Nice. So then we relax all the edges incident to the sixth vertex, yeah, and we set new distance between these vertices and source, and then we need to relax all the edge incident to this vertex, but it don't change distance. If you see, yeah, you see that my 22 plus minus 30 is equal to minus 8, and it is bigger than minus 11, and we have no other edges in this between these vertices. So in the end of our algorithm, we get this array of distances, and we see that we have no passes between S and first and second vertices, and we have passes between source and other vertices, and we have we know now the distance of it, the weight of it. Yeah. Okay. And we see that if we relax all the edges, in some way we get the real distance between vertex and source. But of course, if we relax the edges in the other order, we get some mistakes. But for example, if you see, we have the shortest path between S and fourth vertex is equal to -3, and it contains only one edge. Yeah. And if we relax all the edges, then we set to the fourth vertex distance equal to -3. If we use order that can be not equal to the topological order of this graph. But if we relax this edge between third and fourth only one time, then our distance will be equal to -3, and it will be equal to delta from S to E. And it doesn't change any time when we relax other edges. Yeah? Because we have no any passes from third to fourth vertex that has weight smaller than -3. Understandable. So after we discuss the next algorithm, we now discuss Dijkstra algorithm, and after it we face with Bellman-Ford's algorithm, and we remember this property of the graph, that if we relax all the edges, then we get some real distances between vertices and source. And if we relax all the edges a lot of times, we can get the true distances between vertices and source for all vertices. And we talk about it after Dijkstra's algorithm. About Dijkstra's algorithm, about idea of it, if we have some set of vertices that we know the real distance between source and it, yeah, we know for these vertices what is the shortest path between it and source. Yeah. Then we can say that if all the edges, it is important, if all the edges if all the edges have weight bigger than 0, yeah, we say that we have some vertices that adjacent to the vertices in the Q. Yeah, I can draw it. For example, 1, 2, and 3. Yeah, and we have H to the new vertices. And we have no other edges between the set of vertices S and set of vertices Q. Okay? It is S and it is Q. S cuts in the network. Do you remember previous lesson? Yeah.
Yes.
So we have, for example, weight 1, weight 2, and weight 3. And we can say that we add vertex V that will have nice. We can compare this number with this number with this number. Yep. And if we know that, for example, d plus 1 or d of 1 plus double v1 is bigger than this number and bigger than this number, for example, yeah, then we say that every path between source and vertex v and vertex v with index 2 and 3 will contains will have weights more than this number. Because if we have path from source, it has some part that contains in set S. Then we go to U with index 1, 2, or 3, and then go to the V. And we know that distance from U vertices to the source is equal to the shortest distance between it and source. Then we say that distance between this vertex and S will be bigger than distance between this vertex and S. And then we say that, okay, we can add vertex V1 and say that distance between V1 and S is equal to this number. Yeah, we say that it is equal to distance V1. Because any path that contains other edges, for example, we can go to the V1 using edge between U2 and V2, will be bigger than distance from source to U2 and plus weight of this edge. Oh, sorry. Of course, it's smaller than other distances. Yeah, I have a mistake. Yeah, and it will be bigger than this distance. Yeah, so we add vertex V1 to the set with this new distance. And then we say that, okay, it is the shortest path between S and V1. It is weight of the shortest path. And then we repeat our algorithm. Yeah. This is steps of this algorithm. Firstly, we say that we have set S empty and Q is equal to set of the vertices. Then we of course, initially say that distance between any vertices and source is equal to infinite, and for the vertex S, we have distance is equal to 0, of course. Then we extract vertex from Q with minimal distance and add this vertex to the S and relax all the edges that are incident to it.
What is the minimal distance? Which
Minimal distance? As you remember, for the previous example, we have red numbers. It is the array of distances between source and other vertices. Initially, it can be bigger than real distance between source and vertices, that is equal to weight of the shortest path between it.
I don't understand how will we define which Q will we extract from Q?
We have array of vertex, for example, or we have binary tree or heap of vertices, and we know for every vertex what is the distance between it and source, and then we say that okay, we can extract U with minimal distance. For example, initially we have distance is equal to infinite, yeah, and we have only one vertex that is source, of course, that has distance equal to 0. And first step will be that we extract vertex S, so that is source, and then relax all the edges that are incident to it. Okay? Then, yeah, do you have any questions? Guys from the...
Yes, can you hear me?
Yeah, I hear.
Could you go to the slide 4 on the left board?
Slide.
Last, no, on the left one, other one. Other board.
Oh, yeah, okay. Yeah?
It's, yes. Here we say that the du1 plus w1 equals to dv1. It means it's the shortest path from S to from S to V, right? To V2.
We know the real distance between source and U numbers. And we say that new distance between V1 will be equal to sum of distance from source to U1 plus double V1. And we say that for all other vertices in Q set, we can say that distance between it and source will be bigger than distance between V1 and source. Because
but in the picture, I think you pass from W2, not from W1.
Can you repeat?
In the picture, you passed through W2, not W1. Why is it so?
That I draw here.
Yes. I think it should be from W1 because it will be smaller.
It was example that, of course, we can have the path between S and V1 that contains edges between U2 and V2 or U3 and V3. Yeah, but if it contains these edges, then weight of this path will be bigger than distance from S to U2 plus weight of this edge. So it will be bigger than this sum, and then it will be bigger than d of v1. Then we say that there is no path between S and V1 that will be shorter than a path from S to U1 plus this edge. And so it is the shortest path between S and V1. Because any other passes between V1 and source, for example, if we have other path we can have a lot of passes from S to V1, but we can say that every path contains parts that connect S with U vertex and contains edge that connect U vertex with V vertex. So every path will be bigger than this sum. So if we want to find the shortest path between S and V1, we say that it will be a path between S and U1 plus this edge. Do you understand, Masoud?
Yes, thank you, Professor.
Okay. Okay, about Dijkstra's algorithm. So, Dijkstra's algorithm has this idea and repeated for all vertices in the queue while we have vertices in queue. Yeah. So firstly, we say that we have for this example, we have 0 vertex. We extract it from the queue. We relax all the edges incident to this vertex. So we set new distance for this and this vertex. You see, yeah? It's equal to 10 because we relax this edge. It's equal to 2 because we relax this edge. Yeah? Then we said, okay, our queue contains all vertices but not source. Yeah? So in the queue we have a vertex with distance to the source equal to 2 and we extract it. Here you can see. We extract vertex 2, vertex with distance to the source equal to 2, and then relax all the edges that start in this vertex. And set new distance for this, and these vertices. Okay? Then we see that for in the queue we have 5 as the vertex with the smallest distance to the source. Then we extract it too. We extract this vertex and relax this edge and this edge. Then we see that 9 it is equal it is the smallest number in the queue. Then we extract it. Then we repeat for other vertices in queue while we have any vertices in the queue. In the end, we have 3 that connects source with other vertices and paths between source and vertices in this tree will be the shortest path in this graph. Okay? So, of course, you can see that this graph contains only positive number weights on its edge. And of course, Dijkstra algorithm has the main disadvantage that it works only for graph with positive weights on these edges. If you have any edges with negative numbers, of course, you can say if we have negative numbers, but we have no negative cycles in our graph. Dijkstra doesn't works with it too. So it is main disadvantage of Dijkstra algorithm that it doesn't work with graphs with, for example, only one negative edge. Okay, and it is a pseudocode of it. Yeah, you can see that initially we set S equal to empty set and Q equal to set of the vertices. Then we set that distance from all the vertices to the source equal to plus infinity, and distance between source and source equal to 0. Then, while our Q is not empty, we extract vertex U with the minimal distance, and then we relax all the adjacent we relax all the incident edges to it. Okay, and about complexities, of course, space complexity equal to O from number of vertices, but time complexities equal to different O notations if you choose different data structure to store Q. Yeah, if you choose, for example, array, yeah, to extract minimal distance, you need to go through the whole array and find minimal. Yeah, and we need to use O from number of vertices operations in one operation extract. And we need to use O from number of vertices operation extracts. Yeah. So we get this bad asymptotical time complexity. So if you use other heaps, it will be better time complexities. But of course we get logarithm from number of vertices. It is a heap with the structure that okay, I think we'll talk about it on the other lectures. If you don't know it. Okay. It's about different representation and implementation of this algorithm. Okay.
It will include binary, Fibonacci numbers.
It uses Fibonacci numbers, of course. Okay, and about the next algorithm, about Bellman-Ford algorithm. For example, imagine that we find all the shortest path between source and other vertices. Then we can order it as, remember when we talk about BFS, we have level 0, level 1, yeah, that contains vertices with path contains only one edge, yeah, that contains that we have level 2, yeah, and etc. Yeah. Of course, now we have weights on it. Yeah. Okay. And imagine that now distance from each vertex to the source equal to infinite, as in the beginning of the previous algorithm. Yeah. And this distance equal to 0. If we relax all the edges in different order, not in the topological order, not in other orders, in different order, if we relax all the edges, then we cannot say any about these vertices, but we can say that distance from these vertices to source will be equal to real distance equal to -2, -3, 4, and 5. Because when we relax this edge, we change this number to -2. Then we change this number to -3 when we relax this edge. And this too. Understandable. And if we know this order, we can say that there is no path that will be smaller than -3 and connect this vertex and this. Yeah? Okay, so then, for example, for this vertex, if we relax all the edges, we have a real distance between this vertex and this vertex. Then if we relax this edge, distance between this vertex and this vertex will be equal to 20 and will be the real weight of the shortest path between this vertex and source. Okay, then we can repeat our relaxation of all the edges many times, and we have boundary to the numbers of the levels. What is the boundary of the number of the levels? Hmm?
It will not be that big.
Hmm?
It will not be that big.
Yeah, we say that it's level 1, level 2. What is the maximal number of level we can see in the graph?
The longest path.
Hmm? Yes, the longest path. And what is the length of the longest? We set S as the vertex that that in the level 1. And of course, it will be equal to eccentricity. Remember, yeah, eccentricity of vertex S, of course. Yeah, remember it. It will be maximal of the distances between S and other vertices. But of course, it will be smaller than number of vertices minus 1.
And it's smaller or equal to the diameter.
Hmm?
It's smaller or equal to the diameter.
Oh yes, of course. But diameter will be smaller or equal to number of vertices minus 1.
Yeah.
Yeah. So, main idea of the Bellman-Ford algorithm that we can relax all the edges and repeat it these times. And then we get real distances between all the vertices and source. So it is a pseudocode of Bellman-Ford. We have the same initial part, yeah. We set 0 and infinite numbers, and then we relax all the edges and repeat it number of vertices minus 1 times. And then we say that in the previous algorithm, we said that graph doesn't have any negative weight edges. But now we can say that, as in the example, yeah, that graph can contain negative weights, negative weight edges, and of course it can contain negative weight cycle. And it's interesting, yeah, it is interesting that if we relax all the edges and then we repeat relaxation after we end these 8 lines, yeah, if we repeat relaxation of all the edges and it changes only one distance, then we can say that vertex that has new distance contains in negative weight cycle. Because we can see on this in this example, yeah, we don't have distance between source and any vertices in this cycle. Or we can say that it is equal to minus infinity. Yeah, and then if we have some distance, we can relax all these edges, and then it will be smaller than this distance. And then, of course, if it is probable that if in the graph we can find negative weight cycle, then when we relax all the edges last time, it changes some distances, and so we find it. So Bellman-Ford algorithm interesting because of finding all the distances, of course, yeah, we find all the distance. But if we cannot find it, if our graph contains negative weight cycle, it works too. It finds it. Our algorithm will find the negative weight cycle. Is it understandable? Nice. Okay. As I remember about correctness, it's about correctness. It's about if there is no negative weight cycle in the graph, then after we repeat this relaxation operation many times, we get real distance. Why? Yeah, as I say in this example, yeah, because we can divide all the vertices into some levels, and we say that if we relax all the edges k times, then we find distance from source to all the vertices that contains in levels from 1 to k. Yeah. Then, if we repeat relaxation of all the edges, for example, we relax this edge, yeah, we find the real distance to this vertex, and we find for all these vertices the real distance from it to source. And then by induction we can prove that Bellman-Ford algorithm solves our problem in correct way. It's about correctness. So, about complexities. Firstly, we repeat relaxation operation for each edge, yeah, and we relax with time number of vertices -1 times, yeah. So we get this asymptotical times of our operations. Yeah. Okay. And about disadvantages of this algorithm, we can say that, of course, time complexity is equal to, if we have edges equal to number of vertices in square, yeah, it will be equal to number of vertices in third power, yeah. If remember first lecture, yeah, if our graph has a lot of edges, then our notation that we use here will be equal to insert. So it is bad asymptotical solution of this problem. And of course, imagine, for example, we relax all the edges and we repeat it number of vertices times, and we have no any negative weighted cycles, but then we change only one edge. For example, this -3 we change to -2, for example. Then we need to repeat our algorithm for all graph. So we have a graph of real data, yeah, that can change many times. It is bad that our algorithm we need to use from start to end, and we cannot separate it into the parts that we can repeat if we change locally our graph. So it of course disadvantage of the algorithm, and if we change, for example, in the Dijkstra's algorithm, yeah, if we change weight of the edge, we can repeat from this edge our algorithm. Yeah, so for the Dijkstra algorithm is preferable to use in cases when we have positive weights graph. But of course, the main disadvantage of Dijkstra algorithm that doesn't appear here, yeah, that Dijkstra doesn't work with negative weights edges, but Melmer-Ford algorithm works with it. And then we talk about Dijkstra speed up and solution of the problem. And today we will free earlier than previously because I have no a lot of time in the evening. Okay, so about Dijkstra speed up. What is the problem that we solve for in the first part of the lecture? Finding the shortest path between all the vertices and the given vertex S. Yeah? But of course, for example, what is the application of this method? For example, if you have a transport system and you want to find the shortest path between two cities, you can use it. Yeah? Because any road has weight as time that you spend when you use that road. Yeah. Yeah. So, for example, if you search some tickets from Moscow, for example, to Berlin, for example, you want to find the shortest path between Moscow and Berlin, between 2 points. Not all the points and Moscow, yeah, not all the cities and Moscow, but between these 2 points. So another problem that we want to solve, and this it is problem to find the shortest path between two vertices, source and sink in the graph. And how we can solve this task. For example, we can start Dijkstra's algorithm, and when we add t to the set S, we can say, okay, we find shortest path between it and S, so we solve our task. Okay, but it is bad because we can find a lot of shortest paths between other vertices and S that we needn't. Yeah. So how to speed up Dijkstra? But of course, it will be speed up in the practice, but not in the theory, because in the worst case, we get, of course, the same time complexity as we see in this table. Okay. So, for example, we can use Dijkstra algorithm and start it from the source and from the sink. Of course, using reversible edges. Yeah, and when we find vertex that will be terminated for both of the algorithm, then we say, oh, okay, that is the shortest path between source and sink. Of course, there is some problems of it. For example, we can draw this example. We have if we have this graph and we say that it is S and it is T, what is the shortest path between S and T? The upper path, yeah? It is the shorter. Okay. So let's start to Dijkstra's algorithm. I write red numbers as distances from S in the forward algorithm, yeah, and we can write these numbers. And then I write numbers, I write green numbers as the distance from T in the reverse graph. So, when we start from S, we say that we relax all the edges that incident to S, and we set this distance equal to 3 and this distance equal to 5. And we terminate this vertex. We extract it from the queue. Then we extract this vertex from the queue of the backward algorithm. And then we relax this edge and this edge. And change these distances. Yeah. 3 and 5, 2. Then we see we don't terminate these vertices. Yeah. So vertex with the minimal distance to the source, it is 3. We extract it and relax this edge. It is 3 and we extract it too.
Here, in both ways, we found common vertices.
Hmm?
Down and up. We found common vertices.
Here. But these vertices will be in both of Q's. But if you see here, when searches intersect and it, you need to understand it like when we extract from both of algorithm Q's some vertices, then we execute our algorithm and end it. Then we see that the minimal number equal to 3. We extract it and we change this equal to not 3, 6, yeah. And this of course 6 too, yeah. It was the false. Yep. Okay. Then we see we extracted these 2 vertices, and for these vertices we say that this vertex has minimal number, and we extract it. Yeah, and set this number equal to that. Okay, then for green numbers we say that we extracted these two vertices and minimal of these distances equal to 5. And we extract this vertex too. Yeah. When we extract one vertex from both Q's, then we terminate and say we have some vertices that have finite numbers in both arrays, yeah, in both arrays of distance, and we find minimal sum of these numbers. Of course, if we say, oh, we extract this vertex from both of Q's, yeah, and then we say 5 plus 5 is the shortest path, we will be false. So we need to compare these numbers, these sums, and say 3 plus 6 smaller than 5 plus 5, then the shortest path that will connect these vertices. Understandable? So, of course, you need to end your algorithm when you extract vertex from both of Q's, but the shortest path can not contain this vertex. We extract this vertex from both of Q's, but the shortest path between S and T doesn't contain this vertex. Understandable? Nice. So, it's about bidirectional search, and in practice it makes smaller operation than usual Dijkstra algorithm. You can use it in the practice. Okay. And about the last algorithm for today, it's about A with star search or goal-directed search. It is another name of this algorithm. It's about similar to Dijkstra algorithm, but it has improvements and it contains important ideas, I think. About ideas. Imagine that you need to find the shortest path between this place and this place. Yeah, and of course you will find paths that will start on the higher place and will be ends on low places. Yeah. For example, we can set weights of these edges equal to distances, but we need to understand that there are edges that connect vertices on the same height, and there are edges that connect vertices on the other heights. Yeah, and these ideas, this idea names as a potential function that we can set for all vertices new function that we name as potential function, and we change weights for all edges from weight from U to V, we change it to new weight equal to difference between this and potential of start point plus potential function of the end point. It will be new function of weights of the edges. Okay? Why we get something interesting. Because if you can see, for example, I can draw, yeah, I can draw some example on the board. Yeah, I set weight of this path equal to weight 1, weight 2, weight 3, yeah? It is the sum of weights on these edges. And then when we change weight of the edges and we summarize new weights, then we can say that new weights will be equal to weight of this path in the initial graph minus potential function of source plus potential function of thing. Why?
How would we know potential function?
It is interesting because, of course, in the common way, potential function doesn't change anything. But if we have, for example, country and networks in the country, we can say that potential function equal to height of the area, for example, and we find potential function in empirical way, of course. Or for example, we know that our graph equal to two-dimensional lattice, for example, yeah. This. And then you can set some empirical ways to set different potential function in these cases. Of course, potential function you get from outside your algorithm, and in the algorithm you think that you have already had the potential function. And then you can see that it is equal to W minus some constant, and you can see that it will be equal to this, and it will be equal to this. And then we can say that we change all the weights with the same constant. So if we initially have W2 smaller than W1 smaller than W3, then we can say that this partial order will be the same for the W with overline. Understandable? Because we change with the same constant. Yeah. So, a search will be equal to Dijkstra's algorithm, and when you use weight comparison, yeah, we can see it in relaxed operation, yeah, we use weight in it. So here we use new weights with overline. We put here weight plus minus potential function from U plus potential function from V. Understandable? Nice. Then, yeah. Of course, in the worst case, we don't get speed up. And interesting that it works only if, for example, if we get bad potential function, we can not improve, but disimprove our algorithm, and it can work not quickly than Dijkstra algorithm. So you need to use it if you have empirical way to understand why your potential function is better than 0. Yeah, because if we set potential function equal to 0 for all the vertices, then we get the same graph, and then we get Dijkstra algorithm. Yeah. So of course, if you get potential function equal to distance between this vertex and sink, of course, you improve your algorithm, and it will works only all from number of vertices times, because you find the shortest path from vertex to the sink, and you find it using only number of edges in this path times your operational relaxation. And it is the optimal situation, of course, if you have potential function equal to distance to sink. But in the common way, you get different empiric potential function, and it can speed up your algorithm, but it can get more worse algorithm than Dijkstra. Okay. So it's about a search, and that's all for today, I think. If you have any questions, tell you this question, or we can end. And of course, Masoud, Philippe, and Anda, if you have any questions, ask me. Do you have any questions about Dijkstra or Bonner-Ford algorithm, or about the shortest path problem in common way? Do you understand how to solve the shortest path problem? If we have unweighted graph, we use BFS, yeah, or we use DFS if we want, but DFS we cannot use the we need to use with understand that we cannot use it in the way to solve the shortest path problem. Yeah, only BFS.
No, we can't use D. Because DFS might give you a fast path as maybe.
Because it is depth algorithm, and for example,
I can give you an example.
for example, for this graph, for example, and you want to find from the shortest path between source to sink, and DFS can find this way.
But you can find the other way.
Why? When we use DFS, we choose edge incident to vertex in the random way.
Yeah, it's not always sure that it's going to take S to T. You might get S to T, of course, but it's not. It doesn't guarantee that you will get the shortest path.
Mhm.
But you will get the pass. But
But
it's not.
when we reached the first time here, like we did it like this. Can we go back and apply it?
No, that one is like.
But no, already, yeah, because we already discovered it, yes, so.
Yes,
Yes.
we already discovered it.
Yeah.
So we want to run.
No,
Yes.
So yeah, if we have random graph, we can ask if it yeah unweight, and then we use BFS. If it is weighted, yeah, if some edges is negative weight, so yeah, we use Bellman-Ford. Yes.
yeah.
Okay. So it's all about the shortest space problem, and the next lesson will be about, I think, Cartesian tree, or about heaps. If you don't know about Gushchin heap.
We will have tests, right?
About this? Yeah.
Next.
No, not. I think on the 5th lecture or on the 6th lecture.
Each lecture there is a contest.
Yeah. Because
Now this week we will have a new contest
And-
about.
and you need to use Bellman-Ford's algorithm and Dijkstra algorithm in practice.
Yeah. Interesting.
Yeah, I wanted to ask in the
Yes,
previous lecture.
Hmm?
In the previous lecture.
Oh, what's
In
well?
the previous lecture.
Like the pre.
I have a question about
Oh.
genetics.
Okay.
There was something called time. I can, you know,
I can open
oh,
previous.
to the board. What does time do? I can see what time do, but why do we need it?
Oh, what is the slide that you
Slide
want?
number 5.
Okay.
Time. It's time when we discover the vertex.
Discover the vertex.
Yeah. Time is zero.
Here.
Time is 0. And down it's down, go right. So it's
Yeah. And here.
It's time when we discover the vertex.
Yeah.
Why do we need it?
To discover the vertex.
No, why do we need time?
Why do we need time?
Yes.
To set time when we discover and when we finish it. Of course, in the application you can use this time, and as you can see, we use it in the topological sort. Yeah, because and for finding strongly connected components. Remember it. When we use a diffs, we get finish time of it, and then we repeat diffs in the graph when we reverse all the edges, yeah, and start with the vertex with the biggest number of finish time. So we use it in this way, for example. About discover time, quickly, I cannot remember any example when we use discover time, but of course you need to you need to upgrade your time here to understand how many operations you use. Hmm?
Why this last line 21. U.f time
Yeah,
to
yeah. Finish time. It is discover time, and it is time when we finish to explore adjacent vertices to vertex U. So in the application you can use it, because yeah, if you don't need discover time or finish time, you can drop this row from the code. But in the common way, in the results of DFS, you get tree, DFS tree, yeah, as in the example here, yeah, you get DFS tree and get to erase discover time and finish time, and in different way you can use one first time or second time. Okay, are there in the chat? Do you have any questions? No? Okay, that's all for today.